basically with the talk about the work I did together with Susanne. And my talk will be mainly about the continuum limit, but I will also talk about some other aspects. First of all, Susanne told you that I will tell you, no, one slide. One slide. So again, yeah, there were many conceptual questions in quantum geometrodynamics that made the progress stall in this approach. And our new proposal, as I told you, we restrict to on the classical level to a phase space of functions that are piecewise constant. And we suggest a new canonical quantization procedure that makes the metric positive definite. And what we have to do now is to quantize these discretized constraints. We can use the generalized wild quantization, which I will tell you in a minute. And there's also a way to quantize approximate gauge transformations. And then we have to study the continuum limit. So first, generalized wild quantization. You may know the formula for the Schrödinger representation. It works well. It is a way to, by the way, there's a factor 1/2 missing here. It is a way to quantize general functions on phase space in such a way that if you insert polynomials, then these polynomials are quantized to polynomials again. And in our case, the P operator is only symmetric and not self-adjoint, as you know, for example, from the hydrogen atom, the radial momentum operator. And so there's an adjoint part. And this can be used, for instance, to quantize these quite complicated expressions that arise in the constraints, for example, inverse square roots, as you know. And we can just apply the wild quantization formula to the Hamiltonian constraint on a lattice, which is well defined because we are on a lattice now. It's not possible in the continuum. But on a lattice, it is possible to use this formula to quantize even these complicated expressions of Q and P. Next, I will tell you, so this was mainly for the Hamiltonian constraint, but for the diffeomorphism constraints, we have a better approach because in the continuum, they actually form a Lie group, an infinite dimensional one, but still a Lie group. And this allows us to use a better method to quantize it directly. So we assume, for instance, in order to make it easier for the talk, I restrict myself to a scalar field, and I assume a general expression for the gauge transformation constraint. And I assume that they satisfy a classical Poisson algebra Lie bracket, where this is still a linear combination in the sense of the constraints where there's a difficult function maybe here, like in the diffeomorphism constraint. And then we discretize using piecewise constant functions, and then we get discretized versions of these constraints, and they satisfy a Poisson algebra again with a term that we like and a term that we don't like, because this makes it second class basically, but these etas go to 0 as the lattice goes to the continuum, and then hopefully the approximate gauge transformations will approach actual gauge transformations. So we can solve Hamiltonian's equation of motion to make a finite transformation. So the generators generate infinitesimal transformations, but we can solve these equations to generate finite transformations if these D's only depend linearly on the momenta, which they do for the diffeomorphism constraints. They don't do this for the Hamiltonian constraint. And when we get the Hamiltonian flow for this particular constraint, And it can be interpreted as an approximate gauge transformation. And we can use it to quantize. We can quantize this approximate gauge transformation on a lattice by just evaluating it on the configuration variables. Again, this is possible only because it's first order in the momenta, and so the solution depends only on the configuration variables. And then we have a nice, or not so nice, determinant, a square root of a determinant of the Jacobian matrix here, which makes this into a unitary operator, actually. So it's a couple of calculations, and you find out that it's unitary. And so you can also calculate its generators, which exist by the Stone theorem on unitary one-parameter groups. Thomas Thiemann recently did a similar thing in a related approach, just to give you a reference. And then we can move on to the continuum limit. And what we do in order to study the continuum limit is we have a Weil algebra on every Hilbert space. So it's not really a Weil algebra, it's something different if we insert our new representation of the canonical commutation relations, because it doesn't exponentiate to the Weil algebra, but it can still be expressed in terms of these Weil elements. They will just satisfy a little bit different relations. And but it's still a span of elements of this form. And anyway, I'm talking about the Schrödinger representation in this example. So here it's the actual Weil elements. And then we can take a continuum limit of these lattice Weil algebras, which is given by the inverse limit of these lattice Weil algebras. And we can make identifications, which basically mean that on a lattice, the lattice before the next lattice, you have the phi nk as degrees of freedom, and basically this is the center of mass of the previous neighboring lattice points. And then suppose we find a sequence psi n of states on each lattice, then we can define a state on these lattice Weil algebras in terms of the expectation value. And then we can check whether these omega n form a Cauchy sequence. And if they do, then we can define, so if they do, they converge to something. And then we can define a state on the continuum Weil algebra in terms of the limit of the sequence. So this is how we obtain a state on the continuum Weil algebra. And then we can use the GNS construction to build a whole Hilbert space on top of the vacuum state, which basically, this limit is going to be some sort of vacuum state. And then on top of that, you can generate all other states by repeatedly applying Weil elements and their linear combinations. And then we want to quantize the gauge transformations on this continuum Hilbert space. The ideal thing you would like to do would be to take this lattice Weil algebra and apply these transformations from both sides in order to get the transformed elements, but unfortunately they are no longer in the Weil algebra itself, so it's a little bit tougher to take the continuum limit on of these objects. because you cannot simply insert them into this state here anymore. But what we can do is we can, suppose we have a state psi in the continuum Hilbert space. Then we choose a sequence psi n of stage such in the lattice Hilbert spaces such that the algebraic states associated to them in the way I described earlier converge to the algebraic state described by the state in the continuum Hilbert space that we are interested in. And then we can expand those states, so the approximately gauge transformed states on the lattices in terms of these Weil elements on the lattice, because the representation is irreducible, and so every vector is cyclic, and therefore such an expansion must exist. And then we can define the gauge transformed continuum state by taking the limit of these objects applied to psi, where if you want to express it really rigorously, you need to put some equivalence classes. All right, so let me summarize. We used a generalized Weil transformation for quantizing the lattice version of the Hamiltonian constraint. We have a way to generate approximate gauge transformations in the discretized theories using the Hamiltonian flow. We can quantize them on the lattice Hilbert spaces, and we can take a continuum limit of states on these Hilbert spaces using this Cauchy criterion, and we have a method of taking the continuum limit of these approximate gauge transformations with some caution to be taken care of, because of course I missed out some details that need to be made rigorous. And the outlook is, so we still need to figure out a way to take the continuum limit of the Hamiltonian constraints on a lattice. And as I told you, there's still not everything done in this approach. It's rather recent, and there's still a lot of estimates that need to be done to prove convergence and things like this. And with this, I thank you for your attention.
Thank you, Thorsten. Question?
As far as I understood, you take a regular lattice to, and that's not a good idea in quantum gravity, because regular lattices, they are good in QCD, where you have